people who are working in differential equation. Am I audible? Okay. So, I will be delivering two talks here. So, first talk is about the this contraction principle and its extension, and then tomorrow I will be talking about its applications, and that will be on differential equations and mostly integral equations, because all those differential equations are then converted to integral equations and then apply the usual fixed point theorems there, where whatever is applicable there. Okay. So, I will start with the basic that contraction principle and then talk about its extension today. So, the as you know this what do you mean by a fixed point? So, you have a certain set x, or let us say you have a space x and then there is a set M. Usually space will be this X space will be a Banach space, and this M will be a closed subset or subspace of that. So, therefore, in its when you restrict the topology of X on M, then it will also be a Banach space, as it is a closed subspace. Okay. So, and then there is a map from this space into this M itself. So, we call it self map, and we say that a point x in M, if it satisfies this equation that T x equal to x, we say that x is a fixed point. Okay. And so, here the first result in this direction was the this Banach contraction principle. Principle or theorem, but it says that if you have T like this, and here I mean x you can take a metric space also in general. So, we will be taking D rather than the norm of x. So, D is a metric there. So, you have if this D of T x T y for any x y in M, if this is less than equal to k times D of x y, where k is less than strictly less than 1, then we can derive the conclusion that first one is that T has a unique fixed point. Fixed point, we say that fixed point we can denote it by x 0. Okay. So, that means that is x 0 equal to T of x 0, and then you have you start with any x in M and consider the sequence, this the sequence T n x, that means you repeatedly apply T on that. So, since it is in it's a self map, so all these will be in M, and then this converges to x 0. Okay. And third one is that the convergence is uniform if M is bounded. Okay. This with the restriction that M is bounded. Okay. This third can be actually broken into three parts. That is, the first one we will prove all these things, that D of T n x for any x in M, x 0 is less than equal to k to the power n over 1 minus k of D of x T x. okay, for any x in M and n greater than equal to 1. This 3 1 and also 3 2 that d of t n plus 1 x 0 is less than equal to k over 1 minus k of d of t n plus 1 x t and x again for each x in M and n greater than equal to 1. Okay. So, in particular we have this rate of convergence, that is d of t n plus 1 x 0 is less than equal to k d of t n x 0. Okay. So, you can see that you repeatedly can go down to t n of x, that is x 1, like you have there, and you get k to the power n there. So, before I give you the proof of this, there was first extension of this, that was the primary extension by Cassi-Pauli, that was Cassiopauli, double P, I think, double P O L I. What it said that if you consider this d of t n x, d of t n y, if there are for each n, if there are these numbers non-negative non-negative numbers, in fact positive numbers for all x y in M, and such that these CNs are forming the convergent series, okay, then also T has a unique fixed point. In fact, we will show that, you see that because these are convergent, so therefore this is a convergent series, okay, and therefore the nth term will go to 0. Okay. So, nth term there exists some large n such that Cn is strictly less than 1, okay, and therefore for some n this will be a contraction, and we will show that the generalization of this contraction principle, that if for any t, even if it is not even a continuous map, okay, and if for some n, if T n is a contraction, then T has a fixed point. Okay. That also, that is a very powerful generalization, because there, see, if it is a contraction, then it has to be continuous. Okay. And this extension, when you have for some n, t to the power n is a contraction, then of course t to the power n becomes continuous, and by this contraction principle it will have a fixed point. Okay. And that implies actually t also has a fixed point. We will establish that also. Okay. So, this is the first extension of this famous contraction principle. Now, let us look at some examples here also. Tomorrow I will be talking about many more examples. So, if you consider this Volterra integral equation, that u x equal to f x plus you have some lambda there, and lambda at the moment you can merge in this kernel k x y and u y dy. So, if you of course you have a very standard procedure, you define the iterates like this. So, you take maybe u0 of y equal to f u0 of x equal to, or simply as a function f, and then define u1 as u1x as f fx plus 0 to x k x y, and then u0, that is, so you write here u0 f whatever u0 y dy, and like that you take the subsequent iterates, that un plus 1 x equal to f x plus 0 to x k x y u n y dy. See here u x is unknown because it is appearing here as well as here, okay, and therefore, this is an integral equation. But here each ui's are known because u0 you started with this with a known function, and then u1 is now known, okay, and so all these are known functions, right. So, you generate a sequence, these are and then depending upon the conditions on this, you actually can show that this is a Cauchy sequence, and then therefore, if you are considering it in like the function space C continuous functions or L2 function L2 space, then if you consider like x as C of let us say if you take it in 0 1 for simplicity, and maybe in complex valued functions, and this is a Banach space, and you if you get these under certain restrictions on this, un going to be a convergent sequence, and that the limit will actually be satisfying the integration. That is one way of approaching this problem. The other way is you look at it as a fixed point problem. So, you define that t of ux, or you consider this equation ux equal to f plus or t of ux, which is f plus fx plus this integral operator, we define it as k of u, okay, u of x. What is that integral operator? So, here actually we put that lambda here, okay, separately rather than merging it in this, and so you put this lambda here also, okay, and then you consider this t of u1 minus t of u2, okay. So, that f will cancel, and you will have lambda, what is that k, actually I did not define, k of u or any function f at x is integral 0 to x, and this k x y f y dy, okay, for any f, this need not be this f, any, or let us say some g here, okay. So, then this you see that you get lambda and k of u1 minus k, this is a linear operator. So, you can write it as does not matter, you can take write like this also, and so if you take the norm, then this is less than equal to lambda mod lambda, and then you have this norm k of norm u1 minus norm, okay. These are all L2 norms there, or maybe C norm, or that x, whatever x we take. If you consider this as a space, or we will see that we can generalize it for this one also, later on we will generalize it for this. At the moment you take this one, and so these are all the supremum norms, okay. And you see that we will assume that this is going to be a continuous. If you take this as a continuous function, then this k will be a bounded linear operator, okay. And so you can calculate its norm in fact, and this for a small lambda this will act like our k. If you write this thing as k, then if you choose for a small lambda, you choose it in such a way that, or this lambda such that mod lambda is less than equal to 1 over norm k, whatever that norm k is there, then you see that this will be a contraction map, okay. So that's another way of looking at this problem, and you see that it will have a unique fixed point, and that fixed point is obviously going to be a solution of this integral equation, okay. So that is one simple application in this case. Later on tomorrow I will see that how we generalize it for this kind of space also. Now let us look at this contraction theorem and then talk about its various extensions. So let me state that clearly here, this Banach contraction theorem or principle, whatever you call it. So we will do it for a metric space. Let MD be a complete metric space. Completeness is essential here. Metric space, and let T be to N be a contraction, okay. Then there exists unique x0 in M such that T of x0 equal to x0, and that was the first thing. And second one is for any x in M, this limit n tends to infinity, Tn of x equal to x0, and then the last one. Of course, we will see that those three different parts of the third one also we will see it separately, but for this in a general setting you have this one as d of Tn of x x0. This is less than equal to k to the power n over 1 minus k d of x tx, or that call that as x1 will, okay. Now let us see the proof of this. So since T is a contraction, so you have this d of T x T square x is less than equal to k times d x Tx, okay. Now you add this dx Tx, you add on both the sides. So what you will have is dx Tx plus dtx T square x is less than equal to k dx Tx plus k times this one. Okay. So, you take it this on this side. So, you will have and then divide it by that one. So, you have d x t x is less than equal to 1 over 1 minus k d x. I think I missed, yeah, this one. Did I make a mistake? Okay.
How do you get that k?
1 minute minus. Yeah. Let me see. I think I made a mistake there. 1 minute. Huh? See, this one is okay because you have this is all right. You add this dx tx on both the side. So, you have k, sorry, this, yeah, this is all right. Okay, that is what I made a mistake there. Okay. Yeah. So, now I take it on this side. So, I have 1 minus k dx tx is less than equal to dx tx minus d tx t square x. Okay. And then I divide this thing on this other side. I have this 1 over 1 minus k here, 1 over 1 minus k here. Okay. Now, I define another function psi x, because we will need that. Of course, you do not need this kind of calculations, you can directly do it without that, but since we will need that kind of function later on also. So, we take we define a function phi like this, phi from m to this r plus is the non-negative reals. Okay. So, by this, that phi of x equal to this side 1 over 1 minus k of only this d of x dx. Okay. You define phi x like this, then this inequality can be written like this, that there is some light problem here. Okay. So, then that thing can be written as dx tx is less than equal to this phi of x minus phi of tx, can be written in this simple fashion. For this is true for any x in M. Okay. Now, so this we can then for a general thing we can write like this, T n x and T m plus 1 x. So, what you do is you write T n x T m plus 1 x, and I mean you like this, you write d of T n x and then T m okay. So, let me write that and then explain it. So, you write this as sum over I equal to n to m d of T I x and T I plus 1 x. Okay. Just adding and subtracting those terms, you keep on doing here. These are n and m, general n and m. Okay. So, T n and T m here m plus 1. Okay. So, then you see that you start with n and then you get Tn and then Tn plus 1 here, and by triangle inequality you will keep on writing those things till you end up with the last that one. So, it is a kind of telescopic sum you will have, and which is then each one using this you can write it as phi of Tn x minus phi of T m plus 1 x. Okay. Is this clear? Because each term you write using what you have done here, okay, using this phi there, okay, and then those intermediate terms will cancel each other, and you will have the first and the last sum. This is called telescopic sum. Okay. So, that is what you will have finally. Now, here you see that this goes to 0 as m tends to infinity. You keep n fixed and let m tend to infinity, because of that each time you will have key k there, and you will keep getting k to the power m at the end. Okay. As n m tends to infinity, k being less than 1, this will go to 0. So, you will have, then what you can do is you take n equal to 1 here and let m tend to infinity. So, you will have this sum, then you can write like this, that 1 to infinity d of T I x T of I plus 1 x, which is then less than equal to phi of T x, and which is a finite term. This is strictly less than infinity. Is that so? Here we have this infinite sum of non-negative numbers bounded by this finite quantity. So, this is a convergent series, okay, and therefore, its remainder can be made as small as you want. Okay. So, by this you can conclude that this Tnx is a Cauchy sequence, right. I mean, what do you mean by that? Tnx is a Cauchy sequence. Means that what? That anything being Cauchy sequence means what? That for every epsilon greater than 0, there exists some index n, such that for n m greater than equal to this capital N, this d of T n x T m x is less than epsilon. That is what you need to show, okay, in order to show that this is a Cauchy sequence. Now, here so again you do that here you let us suppose that this m is bigger. You can, without loss of generality, you can take m to be bigger than n. So, let us take like that, and then you do the similar thing here, T n and T n minus T n plus 1 and go up to m. Okay. So, and so that is you see that that will be bounded by, this thing will be then bounded by going I mean little n equal to capital N plus 1 to infinity, right, up to m only first, and then you can, because these non-negative terms, so you can go to infinity, right. So, that will be less than this, right, and so since this is a remainder of this convergent series, and therefore can be made as small as you want by choosing this capital N to be large enough. Okay. Take any epsilon and then make this quantity to be less than that for any capital N, and then when you choose this n and m, then this quantity is less than that, and therefore, it is a Cauchy sequence. Is that clear? And so, since this m is complete, and therefore, this will converge to a point in that. So, that is the first part you have, and then conclude that that is a fixed point. So therefore, this limit n tends to infinity Tn of x is some point x0. Okay. Now we will show that this is a fixed point. Now here this x0 is actually limit n tends to infinity Tn of x, and that is also limit n tends to infinity of Tn plus 1 x. Okay, because it doesn't matter which point you start, Tn or Tn plus 1, all they are going to right to the same point, right, x0 only. And so now you take that 1 t, and being continuous you can take, so you can write it as t of this thing, and t being continuous you can take the limit inside, and so t limit n tends to infinity of x Tn x, and this is x0, so this is t of x0, so x0 equal to tx0. Okay, so this x0 is a fixed point. Now you need to show that this is unique. So let's suppose that y is another element. So suppose that there exists y in M such that t of y equal to y. Now but then this x0, which is actually Tn of limit n tends to infinity Tn of you can start with anything, or let's say, because what happens then, you have Tn of x, and that is also limit n tends to infinity, because what happens, this is so you have t, you keep on applying this is t to the power n, y will also, this is a constant sequence. Okay, this is a constant sequence, and therefore that will also be going to, you can start with any point we started, and that is going to be Tn of y, which is a constant sequence, and therefore this is equal to y. Okay, so x0 has to be equal to y. Okay, because you, this is showing that you start with any x, it is going to x0. So therefore by this you, same way Tn of y will also go to x0, but this being a this being a fixed point, this is a constant sequence. Each time you apply, because you see ty equal to y, and this t square of y equal to then t of y equal to y. So it's a constant sequence, so it will go to actually y only. So here one thing we are, by this process we are showing that you start with anything, that sequence, when you generate this sequence Tn of x, it goes to x0, and this part we are saying that because of this, that is a constant sequence, and it is actually going to y. Okay, so therefore both the limits must have to be x0. Okay, now the rate of convergence. Now again we look at that inequality, that d of Tn x Tn plus 1 x is less than equal to phi of T n x minus phi of Tn plus 1 x. Now so letting n tend this okay, rather here you have m, I should have phi of Tn plus 1, that was okay. see this we had shown that when we defined that phi, we got this inequality, right. So, look at that inequality again, and let n be fixed and let m tend to infinity. So, then we have okay. So, then this will go to x 0. So, d of t n x, this is going to x 0, and this one was going to 0, and you have t n of x. But what is phi of t n x? This is by definition it is 1 over 1 minus k of d of the phi of x is what? Phi of x we will call that is d of 1 over 1 minus k d of x t x, right. So, for this you have phi of t n x t n plus 1 x. Okay. That was one of the those conditions which we needed to prove, and then here keep on applying that the contraction inequality, you will get k to the power n. So, this is less than equal to then k to the power n over 1 minus k d of x t x. So, that is the one we had to finally prove the rate of convergence of that. And then there were other parts like let us recall what were those one. So, now if you replace this by t n plus 1, then you have okay. So, d of or let us say the last one which we wanted to show that d of t n plus 1, that is more important than this one. This we wanted to show that this is k d of t n x x 0, that is giving you the rate at which it is decreasing. Okay. So, here this is same thing as d of t n plus 1 x, but now x 0 is a fixed point, and therefore, this is equal to t of x, and then you simply get this by the contraction property, you get k of d t n x x 0. Okay. So, that proves the thing. Okay. Now, so this is a very powerful result. It not only gives you the fixed point, but also how those are it gives you a way of constructing finding that fixed point also, and how that convergence is actually being reflected. I mean, the rate of this convergence can be seen. So, that actually becomes apparent because what that number k is. If k is smaller, of course, the rate will be faster. Okay. Now, here in most of the applications, when you calculate these, so how you are generating, you have any you starting with any x, and then you are taking this t x as x 1, okay, and then x n plus 1 as t of t n of x, right. So, when it is 1, you get 1, and okay, t n, I think, all right, t n of x, or yeah, t of let me write it as x n. So, this you have a sequence, either you write it as the sequence x n as t n of something, or you write this sequence x n like this being generated like this. Okay. either this one or you have a sequence Tn of x, for any x, both are equivalent. Okay. So, now in many applications these Tn or these xn's are not exact the values of T. See, T will be certain operator, and like an integral operator you may have to numerically calculate those. So, you may not be knowing exact value, but certain approximation of that number, okay, or that function. So, the important next result is what tells you that how actually even in that approximation it ensures that these errors in your approximation do not grow. That will also converge to the same fixed point. So, I will state that and then prove that result. So, what you have again this MD metric space, and T from M to M, it is a contraction, and with the contraction constant. So, I mean here this T of x minus T of y, d of T of x T of y is less than equal to k times d of x y, where k is less than 1. So, that contraction constant we are denoting by k. Now, supposing that we know that, so therefore, there will be a unique fixed point, and let us denote, let x 0 be the fixed point, of T in M, and let a sequence of numbers, positive numbers epsilons be a sequence such that this epsilon n is tending to 0 as n tends to infinity, and let us say that y 0 is in M, and the sequence y n is contained in M, satisfying d of y n plus 1 of T of y n is less than equal to epsilon n for n equal to 1, 2 and so on. So, what it is saying that this T of y n, which we are denoting as y n plus 1, is not exactly y n plus 1. By our approximations, our y n plus 1 is close enough to this T of y n, okay, because we are calculating that, and in this process there are some errors being creeping in, and but by some way we have an estimate of those errors, and we have that these are less than this epsilon n for each n, okay. And we know that as we keep on approximating, these errors are actually going to 0, okay.
It is approximate sequence of the original sequence xn.
Yeah, so you started with the y 0 and then you generated that this y n's, okay, and this T of y n's, but y n plus 1 is not exactly equal to T of y n, but rather kind of approximate. So, each time you started y 0 and you calculated y 1, T of y0, it is not actually equal to y1, but it's an approximation of no, T of y. So y1 is approximation of T of y0, likewise all others. Okay. Then we conclude, so this is the thing, then this limit n tends to infinity of yn is actually equal to x0. Okay. You started with any y0, and by the Banach contraction principle you know that that sequence has to go to x0, right. But since because of your calculations errors, each time what you are doing, you are not getting exactly, so T of yn is not exactly equal to yn plus 1, but some approximation of that, right. So I mean, then we in general we can't say whether that is yn will go to same point x0 or not, but this theorem ensures that it also will go to that fixed point x0. So in that sense it's a very nice result. Now let us see that.
So space is complete, right?
Yeah. I did not write that. Okay, yeah. This complete metric space. That's a must actually. Sorry. Thanks for complete. Okay.
In this way, sir, we say sequence is stable.
Yeah, it's stable. Yeah, in that. Yeah. In numerical no parlance, it is. You can say that. Okay. So now this proof of this. So we will take that y0 as our any x. So in our earlier terminology, that y0 is any x. Okay, and so then otherwise I don't need to write each time different notations. Okay, so d of then t n m plus 1 x y m plus 1 actually less than equal to, by triangle inequality, d of t m t of t m x, okay, and t of y m, you add and subtract like that, and then by triangle inequality you get t of d of t y m and y m plus 1. Okay. And since this is less than by our this condition, it is less than epsilon n. So less than equal to d of so here you can use the contraction thing. So k t of t m of x and y m, and this is plus less than epsilon m. Is that clear? This thing from you have for ym you get epsilon m. Okay, if I have, yeah, n is replaced by m there, and here you take one t out and then apply that. Okay, this you added here like that. Is this clear? So you, yes. Now
Yn is not a Picard sequence in this case.
no, it's
not a Picard sequence.
no y0, you see you have y0 and then you take t y0, that should have been y1, but it is not exactly equal to y1. We have some y1 which is close to t of y0 like that. So you are taking slightly, no, I mean it's because of our calculations errors and all. Okay, so that's how you have those sequences there. And now here this can be, then you can go down to this last one, and so this you can write then by iteratively you can write this as I equal to 0 to m this k to the power m minus I epsilon I. Okay, so here you have T m and y m T m plus 1 ym plus 1, here you Tm ym, and then recursively you go down to that one, and so you each time you will keep on getting these epsilon i's times those k's there, and so this is what you have. Okay. Now, so by this what you have is d of ym plus 1 x0 is less than equal to d of ym plus 1, again you add and subtract tm plus 1 x plus d of tm plus 1 x x0. Okay. And so this part by our this thing is less than equal to summation I equal to 0 to m k m minus I epsilon I plus d of t m plus 1 x x 0. Okay. Now let us, this goes to 0, so we don't need to bother about this. Let's look at this one. So that part can be seen like this. So since these epsilon n's are going to 0, so there exists some n such that these for given any epsilon, these epsilon given any for any epsilon greater than 0, there exists n like this, such that epsilon n's are less than equal to epsilon for all n greater than equal to capital N. Okay. So then you break this one, and assuming that m is larger than this one, and so I equal to 0 to m k m minus I epsilon I can be written like, you break this sum from I equal to 0 to capital N and then capital N plus 1 to m. So this is equal to summation I equal to 0 to n k epsilon k m minus I epsilon I plus summation n plus 1 I equal to this thing n plus 1 to m, and that is k m minus I epsilon I. Okay. So for these epsilon i's are less than epsilon. Okay. So you can take that out, less than equal to here, and here what you do, you here you write this as k to the power m minus you take out m minus capital N, and then here you will be left with n minus I. Okay. You take out this k m minus n here, and then n will be here, so it's okay. Now this is something okay, this is a finite sum, some finite quantity, because this is a finite sum only. Okay. And so this is overall it's a finite number, and as little m, this m tends to infinity, this will go to 0. Okay. M being of course larger than capital N, and so k being less than 1, this will go to 0, right. And so therefore, and this you can then take less than equal to n plus 1 to infinity. Okay. And so it will be like 1 over 1 minus k only, right, bounded by that. So you have times epsilon. So this thing is then, so that is going to 0. So as m tends to infinity, this will go, this will be bounded by, as m tends to infinity, you what you will get is so limit m tends to infinity of summation I equal to 0 to m k m minus I, epsilon I is less than equal to epsilon, and that larger, that one you will take out up the first term from all, and so you will have, or that sum is actually simply a little this k to the power n plus 1 over 1 minus k. Is that okay? Right? Is this clear? So the first, I mean, that you take out, and then it's like 1 plus k square and so on, and that is 1 over 1 minus k, right? And so again this is a finite quantity, and so it is bounded by a small quantity, right, epsilon. Since epsilon is arbitrary, so this limit will go to 0. Okay. So that's what we wanted to show, that it will show that because this term is going to 0, right, and this we have shown that this is actually also going to 0. So we finally get that this limit m tends to infinity d of T m plus 1 x 0 equal to 0, and this was nothing but that y 0, right. We started with x equal to y 0 only. So that's what we want to show. Now the next result which I will be using tomorrow also is what I talked about in the first extension. That again MD is a complete metric space, and T is from M to M such that T to the power n, or rather we will write it capital N, T to the power n is a contraction for some n in the natural numbers, then T has a fixed point. So here we have I mean no condition on T, right, okay, no continuity or anything. No. So by our Banach contraction principle, this T n has a fixed point. So there is some x such that T n of x equal to x. Now then by this, then you go to T n plus 1, T n plus 1 of x equal to T of T n x equal to, or rather T n of T x equal to T x, right. So then T x is also a fixed point of T n, right, but T n has a unique fixed point, and therefore x and T x must be equal, right. So this implies that by uniqueness of the fixed point of T n implies that this x equal to T x, and therefore x is a fixed point of T. Is that clear? It's a very simple proof, but it is quite powerful, as you will see tomorrow. That's what we are going to use. Now one would, there are many extensions of these results. So, one would like to see, can we relax this contraction condition, like if this result has relaxed contraction condition in fact. So, in more general sense its answer is no, but there are no, under certain additional conditions you will have, other than this result you have. Of course, here is the additional condition is that t to the power, there has to have some n like this, that t to the power n is a contraction. That is also quite a restriction on that in some sense. So, the next class of these conditions, what you call is contractive conditions. So, even for that I mean the result is not in general true. Okay. You need some additional requirements. So, let us see that result first and then talk about that contractive conditions and many results, many extensions using that. So, this example is, I mean you just relax a bit. What is a contractive condition? That d of Tx and Ty is strictly less than d of x y for x not equal to 1. Okay, because if x equal to y, then this is going to be 0, this of course is also 0. So, a strict inequality cannot be there. So, this condition is meaningful only for x not equal to y. So, it is called contractive condition. T is called contractive. See, if it is a contraction, then you have some k there or alpha, whatever you call, and that alpha is less than 1. But in this case it is 1 here, and so this is actually called contractive. That is called contraction and is called contractive. Okay. So, let us look at this example that in this case in general you will not have a fixed point. You need certain additional requirements. So, you consider let us say m equal to, in this case is C01. And you consider this m, rather this set m, set of all f in this such that f of 1 equal to 1. Okay. So, elements in this are continuous functions on 0 1 such that f of 1 equal to 1. Okay. That is the requirement, additional requirement for this m. Now, and define this t from m to m by this, that t of f at t equal to tft, the multiplication operator for any t in 0 1. Now, we will show that this is a contractive map, but it does not have any fixed point. Okay. So, this condition does not guarantee a fixed point, like that contraction theorem, you have always a unique fixed point. So, if you relax it a little bit like that, you do not guarantee, you do not have a fixed point. Now, how do we prove that? So, let us take so here if you look at this t for any f and g in M. So, what is T f minus T z, T f at t minus T g at t.
Sir, you can skip this one, we already discussed this.
Achha, this example you discussed. Okay, then fine.
Fortunately, this is in the
maybe 2 days. Okay, okay. Yeah, that's a nice example.
Nice
Yeah. Okay, so you know it. Okay. So, let us look at then the other result.
Okay. State, then we can stop.
Yeah. Okay. So, okay, we will then skip this part. Okay, so then now first then when does this guarantee, what is that additional condition? the first result is that M is actually a compact metric space. Okay. So, that is the result, that this MD be a compact metric space, and T from M to M be contractive, then T has a fixed point. T has a fixed point. And also fixed point, unique fixed point. T has a unique. Of course, whenever contract condition is, fixed point is unique, that you can easily see. So, unique fixed point, moreover, and you have this limit n tends to infinity, T n of x equal to x 0. Okay. So, here we define a similar map like we defined phi, we define psi, because we get rid of that denominator here and consider only that. So, proof of this is very simple, two-step proof. So, I will finish this and then stop. So, you define psi of x equal to d of x t x. See, earlier we had 1 over 1 minus k there. So, we will give another notation psi x here. So, then psi of t x 0 is d of t x 0 t square x 0 one thing is actually this because it's a contractive thing. So, this let us look at first. Okay. One thing, this psi is actually it's a continuous map, because D is a continuous map, right, distance function, and it is bounded below, and because of okay, what is I am missing? Okay, psi is continuous and bounded below, so it will assume a minimum. So, let us take psi of x 0 be minimum, of psi of x on x belonging to M. Okay. Now, if t of x 0 is not equal to x 0, supposing that x 0, if t of x 0 is x 0, then we are done, and suppose that this is not, then you look at these things, then you have this as okay, yeah, since okay, because t square, okay, now this is simply less than equal less than 1 minute, less than d of x 0 t of x 0. Okay. Now, so this is now psi of okay, psi of x 0. By definition, it is psi of x 0. Is this clear? Psi of Tx 0 is this, and because here there is a contractive condition, these again you have this is not equal to this, and then you get these things like this, and this is equal to psi of x 0. Because if this is equal to this, then again you get a fixed point. So, assuming that is not, you get this, and psi this is equal to psi of x 0. Okay. But psi of x 0 is minimum. So, but you are getting t of x 0 another point, since it is not equal to x 0, which is less than, which is a contradiction. Okay. So you actually cannot have this, and therefore this cannot be possible. So this has to be a fixed point. Now only thing that limit thing is what is required to prove. So do I have time or to prove it? Huh?
Proof we already.
Acha, you are already. Okay.
Adjusting theorem.
Okay. Huh.
This is the
Yeah.
adjusting theorem,
Okay.
So maybe you can skip.
So I will stop here then. Okay. If you have any questions, otherwise. Okay.